then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Okay, greetings pre-calculus students. Welcome to lesson number 14. We're continuing this journey with continuity. I know I've been using the word continuity, but really been looking more at discontinuities. And that's kind of what we're going to do today. We're mainly going to look at the discontinuities that arise with piecewise functions. So our agenda, first thing we'll do is we'll review kind of what we did last lesson, which is finding infinite and removable discontinuities algebraically, and then we'll get into the continuity that we find with piecewise functions. So let's begin our review from what we covered yesterday. Okay, so yesterday we'll have a function something like x squared plus 9x plus 18 over x squared plus 10x plus 21. And it's going to say something to the effect of find the removable discontinuities and or infinite discontinuities, or find the wholes, which are removable discontinuities, or vertical asymptotes, which are infinite discontinuities. And our method is to factor. So I'm going to factor my numerator as x plus 3 times x plus 6. I'm going to factor my denominator as x plus 3 times x plus 7. And then I'm going to see what I can cancel. Well, obviously I can cancel x plus 3. So the value of x that makes that factor 0, which will be -3, is the removable discontinuity, or also called the whole, and also in some areas called the point discontinuity. So again, once you factor and figure out the guy you can remove, the value of x, which makes that factor 0, so -3 plus 3 is 0, that's your removable discontinuity. After you have removed what is common to the top and the bottom, the function is now in its most simplified form. When it's in its most simplified form, the value of x that makes your denominator 0, which in this case is -7, represents the vertical asymptote. Which we also call the infinite discontinuity. I could have just wrote infinite. I didn't write discontinuity here. But that's really the whole process. So as long as I can factor, and hopefully one can factor, and as long as I understand what I remove is removable and what's left at the bottom is infinite, that's the whole process. So let me do one more example of this. All right, so I'd like you to try this particular problem on your own. So now would be a good time to pause the video, try to work it out to find the removable discontinuity and the infinite discontinuity. And then when you start it back, you'll watch me work it out. Okay, you should have been able to find the answer. So let's see, we'll factor the top as x minus 4 times x minus 1. The bottom is x plus 1 times x minus 1. X minus 1 cancels, which makes x equal to +1, removable. And x plus 1 is left in my denominator when it's in the most simplified form. So x equals -1 is infinite, or vertical asymptote. Okay, so that's kind of what we covered yesterday. So let's move on to what's new for today. So today we're going to look at piecewise functions. And piecewise functions are going to give us removable discontinuities or jump discontinuities. they're not going to per se, at least not the piece functions we look at, they're not going to give us infinite discontinuities. And really, it all goes back to understanding how the graph is going to look, something we've covered previously. So I want to revisit how the graph of piecewise functions look as we check this. So let me devise a piecewise function. So let's say f of x is 2x minus 3, provided x is less than or equal to 2. And let's say it's x squared plus 1, provided x is greater than 2. And so when you get a piecewise function, they're pretty peaceful, if you will, except for if anything is going to happen as far as a discontinuity. And I'm speaking of when the pieces are well-behaved polynomial functions, as they're going to be the type of functions you're going to see. So if there's any type of discontinuity that's going to occur, it's going to occur at this value that you see here for these provisions. That's the only place a discontinuity can occur in these type of piecewise functions, where the pieces consist of polynomial functions, because polynomial functions in themselves are continuous from negative infinity to infinity. So it can only happen at this break of the two branches where it could have a discontinuity. So I just want to illustrate the graph of this function to point out what type of discontinuity this guy would have. And basically how the problems are going to be written, they're going to give you this piecewise function. And they'll say, like, it's going to say check the continuity at the given point. So that's kind of a shortened version of the instruction. So I'm going to write that. At the given value, maybe I should say. And of course, the given value is the value expressed here. So we're checking continuity at x equals 2. X equals 2 is not a part of the piecewise function. This is the piecewise function. Now, of course, the answer choices are going to be a jump, infinite, a removable, or perhaps continuous. So I just want to analyze this graph because these are really easy to do. You can look at these and tell the answer. But want to analyze or remind you of the graph so you can kind of see how this works. So here is a Cartesian plane or the coordinate plane. And here is 2 here. And when I go to the left of 2 less than or equal to 2, I'm going to deal with this graph of 2x minus 3. So that's a graph that has a y-intercept at negative 3. 1, 2, 3. And when x is 2, the value of this guy is 1. You plug in 2 for x here, that's 2 times 2 minus 3, you get 1. So 2 points I can plot are 0, negative 3, and 2, 1. Since it says or equal to, I can go ahead and put a closed circle on 2, 1. And so that's that part of the graph. And then all of a sudden, when x gets greater than 2, we use this function. Now, the graph of this function itself, of just understanding it, is just a parabola with a vertex at 0, 1. So it's a parabola that looks something like that. But we're only going to take that parabola from when x is 2 going forward. And when x is 2 for this function, the value is 5. If you plug in 2 for x, you're going to get 5. So let's say 2, 3, 4, 5. So when x is 2 on this function, I get 5. Here the 2 is not included, so it would be an open circle. And then you would continue with this parabola. Now, as you look at this graph, it probably should have been red. But as you look at this graph, what type of discontinuity are you seeing right there at x equals 2? And hopefully you're saying a jump. That's all can occur as a jump discontinuity. And the only way it wouldn't be a jump discontinuity on this type of piecewise function, and by this type, I mean the type that has less than or greater than symbols, as if for some reason these two values when x is 2 were equal. It means this would have came down there and that would have made the function continuous actually. So, but in short, when I see a piecewise function that has less than or greater than symbols, it's going to give me a jump discontinuity. Of course, at the given point. If it asks at another point, like if this problem was asking me to check continuity at say 1 or 5 or 17 or some number other than 2, it's going to be continuous. Okay, so now let's look at what happens if I take this same piecewise function, but instead of less than and greater than symbols, I use equals and not equals symbols. So I'm going to rewrite this same function. So let's say 2x minus 3 when x is equal to 2, and x squared plus 1 when x is not equal to 2. And we'll check continuity at x equals 2. All right, so the understanding will come from the graph. And again, we talked about these graphs of piecewise functions before. And so here is the deal. Again, the most important part of this graph is when x is not equal to 2. That represents an infinite number of values. When x is equal to 2, that's just one value. So the main part of this piecewise functions graph is going to be this graph. That's going to be the majority of the graph. In fact, that's going to be the graph for every point except for when x is 2. So let's look at that. So here is some Cartesian coordinate plane, and let's put a 1 there, and 1, 2. And so when x is 2 at this function, the value of this function is 5. Let's say that's 5 there. But this function, this function doesn't correlate when x is equal to 2. So it's going to have an open circle at 2. So I'm going to put an open circle here at 2. And then I'm just going to graph that parabola of x squared plus 1. So there's that graph. But I do have a value for when x is 2, because when x is equal to 2, I use this graph. And when x is equal to 2, the value of this guy is 1. So I have a closed circle at 1 there. So now look at 2, and what type of discontinuity do you see at 2 here? And the great hope is that you set it removable. So, and you're not going to find anything a little easier than this. So when you have these piecewise functions, I'm trying to show both of them. If they give you equals and not equal symbols, you're going to get a removable discontinuity. It's just that simple. If they show you less than, greater than, you're going to get a jump. Now, and again, that's at the value that they have here. Now, theoretically, it could possibly be continuous at this value, and that is if you plug this number into both pieces and they were equal. So for both these, if I plug this value into these pieces and they were both equal, they would actually be continuous at this number. But none of the problems you're going to see should indicate that. So really, when you do a problem, so now I'm going to do a few examples because this is fairly simple. So f of x, this f of x is 10x plus 14. Provided x is greater than or equal to 10, and 3x squared plus 1, provided x is less than 10. And they're going to say check continuity at x equals 10. So when I see a problem like this, they ask me to check the continuity. I look at the symbols and I write jump. That simple. Again, it's that simple. Now, technically, I should be careful, and I should check if I plug in 10, I don't get equal values, and I don't. If I plug in 10 for x here, it's 114. I plug in 10 for x here, it's 301. So technically, you should check that, but quite honestly, that case is not going to occur. So really don't have to waste time checking that. So just the fact that you see this less than greater than, you know it's going to be jump. Again, when you see this less than greater than, you know it's going to be jump. And simply from understanding how the graph looks when you have less than and greater than symbols. Another example, they tell me, say g of x is x squared minus 4, provided x is less than 8, and x plus 1, provided x is greater than or equal to 8. Excuse me, check continuity at x equals 8. I say excuse me because I didn't mean to write the same symbols, but since I did, I'll just stick with it. And let's see, piecewise function, less than greater than, jump. That's simple. And I'll do one more example. Of course, in my last example, these are going to be equals, not equal symbols. So let's say f of x is 3x squared plus x minus 1, provided x is less than 20, and 5x plus 2, provided x is, I did it again. So this one is provided x is equal to 20, and this one provided x is not equal to 20. And I'm going to check continuity at x equals 20. Keep one on the right, less than, greater than. So when I do this particular problem, I see equals, not equals, and so I know the answer must be removable. Okay, I hope you found that fairly easy to comprehend. That concludes lesson 14. We will see you next time.